And welcome to the deep-fried world of organic chemistry part 3. Strap on your cleats because for the next 2 hours we're going to be throwing a lot at you, including alkene electrophilic addition reactions, reduction and oxidation reactions, alkynes and alkyne addition reactions.
And although you may go insane from all the organic chemistry fun we're about to have, remember that we're on videotape. You can fast forward the tape through sections you already know. Pause the tape if you need to take notes, and rewind the tape if you need to see something again. And if you never want to see us again, weapons of mass destruction work really well.
Now it's disclaimer time. In order to truly understand the intricacies of organic chemistry, you must attend your classes, read your books, and listen to your professors. So go to class, turkeys.
We have a lot of ground to cover in this tape, so start the popcorn a poppin' now and find the remote. So we're going to spend the remainder of this tape covering 10 addition reactions. They are addition of HX to an alkene, hydration, halogen addition, halohydrin formation, oxymercuration, hydroboration oxidation, hydrogenation, hydroxylation, ozonolysis, and oxidative cleavage.
Sounds pretty crazy, doesn't it? But believe it or not, by the end of this tape, you're going to have a handle on each of these reactions, which is good because they're hard to carry. So get ready, because here we go!
Part 1. More electrophilic addition reactions.
These reactions we'll be looking at are all electrophilic addition reactions. They're the same type of reaction we looked at in the deep-fried world of organic chemistry part 2. Remember, they're called electrophilic addition reactions because in the first step of the reaction, we're adding an electrophile to the double bond of an alkene.
We're going to be looking at several types of electrophilic addition reactions. The only difference in these reactions is the type of electrophile participating in the reaction. The key to electrophilic addition reactions is that alkenes are electron-rich. They're Lewis bases, and they act like nucleophiles when they're on the attack. We just look for an electrophile which is ready and willing to react with the electron-rich alkene, just like I'm willing and ready to react with this guy.
You may think that 10 new reactions to learn is just too much.
10 new reactions? It's too much!
It's not that bad. We've already learned one of these reactions, the addition of HX to an alkene. We learned all about that reaction in the deep-fried world of organic chemistry part 2. So, although you may feel overwhelmed by the 10 reactions we're about to look at, don't. It's really only 9 new reactions. Don't you feel better now?
No!
Section A, the first 4 electrophilic addition reactions.
Reaction number 1. Addition of HX to an alkene.
Reaction number 1 is the addition of HX to an alkene. We beat this reaction to death in tape 2, so we'll just quickly review it here. This is the reaction between HBr and 2-methylpropene to form 2-bromo 2-methylpropane.
When the hydrogen bromide approaches an alkene, 2-methylpropene, the HBr molecule dissociates into a proton and a bromide anion. The proton adds at carbon 1 of the double bond, forming a carbocation at carbon 2. The bromide anion attaches to carbon 2, and the final product is 2-bromo 2-methylpropane.
In tape 2, we spent a lot of time on Markovnikov's rule. If you remember, Markovnikov's rule says that carbons with more hydrogens will get more hydrogens, while carbons with more substituents will get more substituents. This is why the hydrogen adds at carbon 1, and why the bromide anion adds at carbon 2. All right, now that the addition of HX to an alkene is fresh in our memories, let's move on to
Reaction number 2, a hydration reaction.
The second electrophilic addition reaction is called a hydration reaction. Hydration reactions are sort of a variation of the first reaction we saw between hydrogen bromide and 2-methylpropene. In a hydration reaction, an alkene, in the presence of a strong acid catalyst, reacts with a mega excess of water to yield a neutral alcohol. Okay, first of all, what's a catalyst? A catalyst speeds up a reaction, but is not used up in that reaction. And alcohols, well, you remember what alcohols are, right?
In the deep-fried world of organic chemistry, part 2, we introduce you to functional groups.
How's it going? Hi. Hey, how's it going?
In the deep-fried world of organic chemistry, part 2, we introduced you to functional groups. A functional group is a particular atom or group of atoms which always behaves the same way in a reaction. The functional group of an alcohol is a hydroxyl group, OH. Now we have to get back to
reaction number 2, the hydration reaction.
Let's look at a generalized example of a hydration reaction. The alkene 2-methylpropene reacts with water in the presence of an acid catalyst, HA, yielding an alcohol.
We've got this alkene, 2-methylpropene, we've got an acid catalyst, and we've got water. The acid catalyst is represented by HA. H, of course, is hydrogen, and A can be almost anything. Most of the time, the acid catalyst used will be sulfuric acid, H2SO4, or phosphoric acid, H3PO4. However, the catalyst is never acid jazz.
The important thing to know about HA is that it's an acid. It's going to dissociate into a proton and an A anion. Like we said, we're not going to concern ourselves with what A is exactly, but we do need to know that once the proton dissociates from HA, then A has an extra electron. It's negatively charged, and it's an anion.
Just like we saw in the first reaction between HBr and 2-methylpropene, when the acid dissociates into a proton and an anion, the proton from the acid catalyst is electrophilic and could really deal with some more electrons.
It sees this juicy 2-methylpropene with a nice-looking double bond. It moves in. As the proton approaches the double bond, it has a choice as to which carbon of the double bond it attaches to. And once again, in this case, the proton will bond to the carbon of the double bond which will yield the most stable carbocation, carbon 1.
When the proton attaches to carbon 1, we say the alkene has been protonated, forming a carbocation just like we saw happen in the reaction with hydrogen bromide.
So, since carbon 1 was protonated, carbon 2 is now a carbocation. The carbocation now needs electrons, and wouldn't you know it, there's lots of water around to provide them. So, water moves in. Its oxygen acts as a nucleophile and bonds to carbon 2. The oxygen now has a positive charge, so one of the hydrogens from the water molecule bails, leaving its electrons and a neutral product behind.
Bye. Goodbye.
Actually, the proton gets an assist from another water molecule. The proton hooks up with a passing water molecule, forming H3O+. This stabilizes the proton until it bumps into, wouldn't you know it, good old A, our anion that was formed when the acid catalyst dissociated. The electrophilic proton adds to the anion, and we get HA all over again, which is the acid catalyst that we started with. So the acid catalyst helps speed up the reaction. is not used up in the reaction and is regenerated so that it can move on to bigger and better reactions.
And voila! HA has formed back up, and we've also got a product. When the proton bailed, it left behind an OH group on carbon 2, and OH is the alcohol functional group. All of a sudden, we're looking at the product 2-methyl-2-propanol. The OH group is on carbon 2, and there's also a methyl group on carbon 2. The name of the molecule becomes 2-methyl-2-propanol. 2-propanol tells us that there's an alcohol group on carbon 2.
So the final product of the reaction is a neutral alcohol, 2-methyl-2-propanol, and we've also got a regenerated acid catalyst, HA. Notice that the product of this hydration reaction has Markovnikov orientation. In this reaction that we just looked at, the hydrogen added to the less highly substituted carbon of the double bond, while the OH group added to the more substituted carbon, so the product was formed right in line with Markovnikov's rule.
There's a shorthand representation for this reaction, just like there was for the first reaction we looked at. An alkene in the presence of water and an acid catalyst, HA, produces an alkane with H added to the less substituted carbon and OH added to the more substituted carbon. The product is a neutral alcohol.
Anytime you add water to an alkene in the presence of an acid catalyst, HA, you'll get a product with an H and an OH group added to the double bond, following Markovnikov's rule.
This must seem like a really quick, really easy way to form an alcohol. But it's not. For all these reasons that we're not going to go into right now, the carbocation that's formed with many alkenes has a tendency to rearrange itself, and you end up getting all these weirdo side products that you weren't even counting on. And you don't get as much desired product as you would have liked, which pretty much makes the whole hydration reaction as useless as a plane without wings.
What do you mean it went down? Did we save the little bags of peanuts?
So instead, organic chemists came up with a different type of reaction called an oxymercuration reaction.
Wow.
But we're not ready to talk about that reaction yet. That's reaction number 5, and we're only at reaction number 2. We need to look at a couple more types of electrophilic addition reactions before we can really understand what's going on in an oxymercuration reaction. So, sit tight. I know you're anxious to get to the oxymercuration reaction, but you just hold on to your horses.
We showed you the hydration reaction now because it's so similar to the first reaction we looked at between HBr and 2-methylpropene. So just remember this little discussion when we get to oxymercuration reactions, okay? All right?
Stop loitering in my park! Get out!
And now the host of Gibberish, Bart Winkdale.
Hi, I'm Bart Winkdale. Let's start by introducing our contestants. Our first contestant is a retinal surgeon from Siegfried and Roy, Maine. Please welcome Mary.
Very pleased to be here, Bob.
Our next contestant is a roller boogie instructor from the year 1975. Please welcome Ken.
Groovy.
Okay, contestants, hands on your bats. Here comes the first word. The first word is transisomer.
Gibberish.
Oh, I'm sorry. That word is organic. You lose 250 points, Ken.
But I don't have any points.
Well then, you'll have to receive a mild electric shock.
Reaction number 3, the halogen addition reaction.
Electrophilic addition reaction number 3 is called a halogen addition reaction. Halogen addition reactions involve the addition of a halogen molecule to an alkene in a non-reactive solvent.
Okay, there were a lot of new words there. First, we know halogens. They're found in column 7A of the periodic table, and they include fluorine, chlorine, bromine, iodine, and astatine. Second, a solvent is the medium that a reaction takes place in. A non-reactive solvent, then, is one which doesn't get involved with the reaction. Non-reactive solvents include dichloromethane, CH2Cl2, and carbon tetrachloride, CCl4.
Remember, Some organic chemist somewhere is carrying out all these electrophilic addition reactions. Of the halogens, fluorine is way too reactive and unpredictable to keep around in a laboratory on a day-to-day basis. Iodine, even though it's a halogen, doesn't react all that well directly with alkenes, so we can scratch it off our list too. And astatine, well, nobody's ever really heard of astatine, so we won't worry about it either. That leaves us with chlorine and bromine as the two halogens alkenes react with most often.
But chlorine and bromine are just regular old halogens. You wouldn't ordinarily think of a bromine molecule, Br, as an electrophile. In this Br2 molecule, the bromines each have 8 electrons. So where's the electron deficiency, huh? How is this sucker an electrophile? How? How, I ask you? Where is the justice?
Remember, alkenes have electrons tied up in pi bonds, and that makes them very reactive. So let's say the Br2 molecule approaches a source of electron density, such as an alkene pi bond. The electrons in the sigma bond of the Br2 molecule are repelled toward one end of the molecule, so the bond becomes polarized. One end of the Br2 molecule becomes an electrophile in a sense, meaning it's low in electron density, because its electrons are hanging out on the other end of the molecule. Our bromine molecule can now behave like an electrophile, just like the proton did in the first reaction we looked at.
Check out what happens when cyclopentene and bromine, Br2, get close together. Cyclopentene has a double bond, of course, and as the bromine comes close to all these electrons in the double bond, the electrons on the end of the Br2 molecule closest to the double bond will be repelled toward the other end of the bromine, causing the bromine molecule to be polarized. The positively charged end of the bromine molecule will be strongly attracted to the electrons in the double bond on the cyclopentene.
Notice that we show polarity along the sigma bond in the Br2 molecule with a delta plus at the positively charged end of the molecule and a delta minus at the negatively charged end of the molecule.
Due to the polarity that's been induced on the bromine molecule, the first bromine on the bromine complex is a little low on electrons, so it forms a covalent bond to the first carbon. The second bromine, realizing it now has 8 valence electrons and a negative charge, decides to get lost, but it doesn't go too far. Carbon 2 over here is now lacking 2 electrons and is like a carbocation. The bromide anion still floating around out there decides to move in on the electrophilic carbocation and form a covalent bond with carbon 2.
Do you see why we call this reaction a halogen addition reaction? We add 2 halogen atoms to the 2 carbons of the double bond.
Add 2 halogens! Did you notice that the reaction pathway of the halogen addition reaction, in which Br2 is added to an alkene, is very similar to reaction number 1, in which HBr is added to an alkene? The only difference between the 2 reactions is that bromine is the electrophile in reaction number 3, and a proton is the electrophile in reaction number 1.
Let's name the product of our halogen addition reaction. There's a 5-carbon ring, so that's cyclopentane. There's a bromine on carbon 1 and a bromine on carbon 2. When we put a halogen like bromine in the name of a molecule, we drop the -ene ending and add O, so bromine becomes bromo. So the name of this molecule is 1-bromo-2-bromocyclopentane.
But there's got to be a shorter way to say the name of this molecule, and indeed there is. You see, there are 2 bromines, and we can indicate this by using the prefix di. The 1-bromo-2-bromo part of the name becomes 1,2-dibromo. The name for the product of our halogen addition reaction between bromine, Br2, and cyclopentene is 1,2-dibromocyclopentane.
Okay, so this is all well and good if we're drawing these molecules on paper. But what do they look like in space?
The fact is, if we could see 1,2-dibromocyclopentane floating around, it would always be found as a trans isomer, meaning the bromines would be on opposite sides of the plane of the cyclopentane ring.
You probably remember from the deep fried world of Organic Chemistry Part 2 that the word trans means that the two substituents, the two bromines, are on opposite sides of the cyclopentane ring. They are across from each other. And you probably also remember that cis means that the two bromines are on the same side of the cyclopentane ring. When two atoms add to opposite faces of the pi bond, they are trans to each other and they have undergone anti-addition. Conversely, if the additions are on the same face of the pi bond, so that they are cis to one another, we say that they have added with syn addition.
Okay, so why does this happen? Why is 1,2-dibromocyclopentane always found in the trans form of the isomer? Basic statistics tell us that when the second bromide bonds to the carbocation, there should be at least half as many cis forms of the isomer as trans. But the cis isomer doesn't form in this reaction with Br2. Why not?
It's stubborn.
The whole truth is, the cis form of the isomer never forms because the intermediate in the reaction is not a carbocation after all. And the reaction pathway is not exactly the same as it was for the one we looked at between HBr and 2-methylpropene. The intermediate in our halogen addition reaction is actually a bromonium ion. Before you freak out, we'll explain. A bromonium ion consists of a positively charged bromine atom bonded to two carbons, and it forms like this.
And here we have our happy little bromonium ion, which we finish off with a little touch over here to make it very happy and special. And of course we have our friendly trees as our neighbors, and another tree over here because this one was getting a little lonely. Okay?
Electron-deficient bromine latches on to carbon 1. It not only forms a covalent bond to carbon 1, but also to carbon 2. It forms this sort of triangular-shaped complex, which is sticking out from the molecule on one side of the cyclopentane ring. So, the positive charge ends up mainly on the bromine atom, but it's also shared by the other two carbon atoms. We call this positively charged triangular-shaped bromine cation a bromonium ion.
Let's take a closer look at the formation of this bromonium ion so we can see where all the electrons go. We'll start at the very beginning.
In the beginning, God created the heaven and the earth.
A little further ahead than that. Oh. A single bromine atom has 7 outer valence electrons. So to fulfill its outer valence shell, it forms a covalent bond with another bromine, forming a Br2 molecule.
Then, like we said, as the Br2 molecule approaches the double bond in the cyclopentene, the bond between the two bromine molecules becomes polarized. As the partially positive bromine atom bonds to the cyclopentene, it forms a covalent bond with carbon 1. At the exact same time, bromine simultaneously forms a second covalent bond with carbon 2. And this is how we get the triangular bromonium ion intermediate in the big middle of our halogen addition reaction.
Here's the point of this whole discussion. Like we said, bromine normally has 7 valence electrons.
Our bromine, this one right here that's participating in the bromonium ion complex, is surrounded by 8 electrons. There are 4 unshared electrons out here, and there are 2 in each of the single bonds between bromine and each of the carbons. So that makes a grand total of 8 electrons. But let's look at how many electrons bromine is actually contributing to the bromonium ion complex.
Bromine still got these 4 unshared electrons out here, and it's contributing 1 electron to this single bond and 1 electron to this single bond. But that's only 6 electrons, and if you remember, we told you that bromine has 7 valence electrons. So although the bromine in the bromonium ion has 8 electrons surrounding it, it's only got 6 of its own electrons, while it usually has 7 of its own. So the bromine in the intermediate bromonium ion complex has a positive charge.
All right, so now we've got this positively charged bromonium ion, and the completely nucleophilic bromide anion is circling, trying to add to the bromonium ion complex. But remember, these molecules aren't flat. The bromine in the bromonium ion complex is sticking out on one side of the plane defined by the cyclopentane ring. The bromine in the bromonium ion complex completely protects one side of the cyclopentane from attack by the second bromide anion. So even if the bromide anion wanted to add to the same side of the cyclopentane ring as the first bromine, it couldn't.
At first, the bromide anion moves in on the same side as the first bromine and tries to add on to that side, but it can't. The bromide anion is actually blocked by the bromine that's already there, bonded to both carbons 1 and 2. Do you see? The bromine that's participating in the bromonium ion complex is taking up all the room on one side of the plane of the cyclopentane. So the bromide anion only has one choice. It has to attack the cyclopentyl ring from the other side.
When it does this, the electrons that are involved in the bromonium ion complex are broken up, and the intermediate bromonium ion complex no longer exists. The bromine that was already participating in the bromonium ion complex keeps a single carbon-bromine bond with one carbon of the former double bond. At the same time, the other bromine simultaneously forms a carbon-bromine bond with the other carbon of the double bond.
So the bromines end up trans to one another, and we say that the addition is anti. The bromines in this molecule will almost always be trans to one another on opposite sides of the cyclopentane plane.
So, one more time. In this halogen addition reaction, a halogen, Br2, is added to an alkene, cyclopentene. As the halogen approaches the alkene, it's polarized. The electrophilic bromine from the Br2 molecule adds to carbon 1 of the double bond and immediately forms another covalent bond to carbon 2. This bromine ends up being positively charged and bonded to both carbons of the alkene double bond.
When the bromide anion hits up the electrophilic bromonium ion, it's got no place else to go, so it bonds to the bromonium ion intermediate with overall anti-addition. And there's our marvelous-looking product, trans 1,2-dibromocyclopentane.
So let's look at the overall formula for reaction number 3, a halogen addition reaction. A halogen, X2, is added to an alkene. For our purposes, X will be chlorine and bromine, and the alkene is represented by this purposefully vague drawing of two carbons attached by a double bond. When X2 is added to an alkene, one of the X's ends up on one carbon of the double bond, and the other X ends up on the other carbon. The two X's add to the double bond with anti-addition.
And that's it. If your professor asks for the end result of a reaction in which a halogen, some sort of X2, is added to an alkene, you'll be able to say that one of the X's ends up on one of the carbons of the double bond, and the other X ends up on the other carbon of the double bond. And you'll also need to mention that the two X's have added anti to each other. Of course, since you're all knowing and wise, you'll also know that this reaction takes place with the formation of some sort of intermediate, be it a bromonium ion if your halogen is bromine, or a chloronium ion if your halogen is chlorine.
So do you see how you can start to apply all of your organic chemistry wisdom here? Once you know the basics, you can predict the outcome of almost anything.
The reaction will yield 1 Hessel methyl flavovusine pepper.
Okay, so we just saw bromine, Br2, come together with cyclopentene to form trans 1,2-dibromocyclopentane. Let's see what happens to this same reaction when we throw a little water into the mix.
Reaction number 4, formation of a halohydrin.
Alkene addition reaction number 4, a halohydrin formation reaction. This is a variation of the hydration and halogen addition reactions we just looked at, reactions 2 and 3. In this reaction, a halohydrin is formed. A halohydrin is a 1,2-disubstituted haloalcohol.
And that means?
Well, 1,2-disubstituted simply means there are two substituents on neighboring carbons. In this case, one substituent is on carbon 1 of what used to be the double bond, and the other substituent is on carbon 2. Easy enough, right? And the term haloalcohol tells us exactly what those two substituents are.
It does?
Yep. The term haloalcohol tells us that one of the two substituents is a halogen, X, and that the other substituent is an OH group. So basically, all a 1,2-disubstituted haloalcohol is a molecule with a halogen on one carbon and a hydroxyl group on an adjacent carbon. And in this next reaction, a halohydrin formation reaction, we're going to find out how to make one of these things.
Basically, in a halohydrin formation reaction, an alkene, such as cyclopentene, reacts with a bromine molecule, Br2. The whole reaction takes place in water rather than in a non-reactive solvent. At this point, the only thing that's different from the halogen addition reaction we just looked at, where we added X2 to an alkene, is that the reaction takes place in water. Other than that, practically everything else is the same. The reaction even starts exactly the same way.
The bromine molecule moves in towards the alkene, and one of the bromine atoms bonds to carbons 1 and 2 of the double bond. And now we have a bromonium ion intermediate, exactly like we did in the halogen addition reaction when we added Br2 to cyclopentene.
The only difference between this reaction and the halogen addition reaction is that the halohydrin formation reaction takes place in water. The other reactants are all still the same. They're just Br2 and cyclopentene. When we added X2 to an alkene in the halogen addition reaction, we did so in a non-reactive solvent, which is a solvent that doesn't get involved in the reaction that's taking place in it. But in this halohydrin formation reaction, the whole thing's taking place in water, and that's a totally different story.
So we've got this electron-deficient bromonium ion sitting in water. And we've also got the bromide anion that was kicked out of the Br2 molecule when the first bromine added to the alkene to form the bromonium ion. Water, with its lone pairs of electrons, acts like a nucleophile. The bromide anion acts like a nucleophile as well. Water and the bromide anion are sort of competing for the electron-deficient bromonium ion. But before the bromide anion can move in to attack, the positively charged bromonium ion intermediate is surrounded by nucleophilic water. The bromide anion never even gets a chance.
Poor sap.
The oxygen of a water molecule comes along, sporting two pairs of unshared electrons. It forms a covalent bond to one of the carbons of the double bond. As the oxygen from the water molecule bonds to one of the carbons of the bromonium ion complex, that carbon simultaneously lets go of the electrons it was sharing with bromine. When that happens, the triangle is broken. Did you see that happen just then? There's no triangle anymore, and we get a regular old, boring-looking, plain Jane molecule. The oxygen atom ends up bonded to one of the carbons of the double bond, and the bromine atom ends up bonded to the other carbon of the double bond.
This achieves several things. First of all, oxygen gives 2 of its electrons to carbon. The carbon's then able to give the 2 electrons it was sharing with the bromonium ion back to bromine.
So the carbons are all happy, and the bromine is happy, but things aren't all good with oxygen. Let's see how many electrons oxygen is actually contributing to this complex. Oxygen gave up 2 of its electrons to carbon to form the covalent carbon-oxygen bond. Carbon takes 1 of those electrons, and oxygen keeps the other electron, so there's 1 electron there. There's another electron in the bond to the first hydrogen, 1 in the bond to the second hydrogen, and 2 remaining unshared electrons, for a grand total of 5 valence electrons. But oxygen needs 6 valence electrons, so it's got a positive charge. It needs 1 more electron to be a happy, stable oxygen with high self-esteem.
Oxygen needs 1 more electron to make the overall molecule neutral. So it boots one of its hydrogens with a little help from its friends, other water molecules. By doing this, the hydrogen leaves the complex as a proton. So oxygen gets the 1 other electron it was looking for, and it's now self-actualized.
If we look at the product of the reaction now, we see the only thing remaining of the initial water molecule is 1 oxygen and 1 hydrogen. And shazam! An oxygen and a hydrogen, OH, make up the alcohol functional group. We said that a halohydrin is a molecule with a halogen and an alcohol group, and we've got a halogen over here and a hydroxyl over here.
Can you believe it? We formed a halohydrin just like that. It was a snap. We've got our wonderful halohydrin product, and the bromine and the OH group of the halohydrin end up trans to each other across what used to be the double bond. So we say that the addition of bromine and an OH group to the alkene double bond is anti.
The addition is anti. The addition is anti.
Let's compare this reaction, reaction number 4, to reaction number 3, the halogen addition reaction. In reaction number 3, 2 halogens were added anti across the double bond, and they ended up trans to one another. And in reaction number 4, the halohydrin formation reaction, the addition of a halogen and an OH group was also anti, so the two groups ended up trans to one another as well. The only difference in the two reactions is that the halogen addition reaction occurs in a non-reactive solvent, and the halohydrin formation reaction occurs in water. Water is a reactive solvent when it's in the presence of carbocations.
You want some of this?
Really quickly, let's name this halohydrin. 5 carbons in a ring and only single bonds, so the main chain is cyclopentane. The alcohol is like a diplomat or something. It's a functional group, so it gets special treatment. It demands to be numbered 1. The main chain is 1-cyclopentanol. The suffix -ol tells us that a hydroxyl group is present, and the 1 tells us that it's on the carbon 1 of the main chain.
But wait! Because the alcohol is a functional group, it will always be at carbon 1, so we can drop the 1 and call the main chain cyclopentanol. There's a bromine at carbon 2, and the overall name of the halohydrin is 2-bromocyclopentanol. Of course, the addition of bromine is anti, and the bromine and the alcohol are trans to each other, so the real name of our product is trans-2-bromocyclopentanol.
So we can see that the overall process of a halohydrin formation reaction is, in water, an alkene plus a halogen forms a 1,2 haloalcohol. If we write this in our shorthand form, X2 is added to an alkene in the presence of water, and the product ends up being a halohydrin, a molecule with an X and an OH on an adjacent carbons via an anti-addition.
The next word is
Organic, organic, organic!
No, I'm sorry, that's gibberish, Mary. You'll have to lose 250 points.
Doesn't she get a shock?
Yeah, could I get a shock?
Just a little one. You know, sometimes there's a fine line between gibberish and organic chemistry. So, does everyone feel extra special educated now? Look, man, maybe we should do a quick review, huh? All right, so far, we've looked at 4 addition reactions. Addition of HX to an alkene, hydration, halogen addition, and halohydrin formation.
The overall formula for an electrophilic addition reaction is A and B react to yield C. Electrophilic addition just means that an electrophile adds to the double bond in the first step of the reaction. Reaction number 1 is the addition of HX to an alkene. The first reaction we looked at was 2-methylpropene plus hydrogen bromide to yield 2-bromo-2-methylpropane. Another way to state the formula for this type of addition reaction is when we add HX to an alkene, H is added to the less substituted carbon of the double bond, and X ends up on the more substituted carbon of the double bond. So the reaction follows Markovnikov's rule. X is the halogen chlorine, bromine, or iodine.
In reaction number 2, a hydration reaction, we threw together an alkene, 2-methylpropene, some water, and an acid catalyst like sulfuric acid, which is represented by HA. In the reaction, HA adds to 2-methylpropene, yielding 2-methylpropanol. What happens is, the proton from the acid catalyst adds to the less substituted carbon of the double bond, carbon 1. A water molecule bonds to the more substituted carbon of the double bond, carbon 2. A proton is kicked off the water molecule, and we're left with an OH group on carbon 2. The product that forms is 2-methylpropanol.
So, the end result of a hydration reaction is this. An alkene in the presence of an acid catalyst, HA, and water yields an alkane with a proton on the less substituted carbon and an OH group on the more substituted carbon. The addition follows Markovnikov's rule.
The third reaction we looked at was a halogen addition reaction, addition of X2 to an alkene. In this reaction, cyclopentene and bromine, Br2, react to yield trans 1,2-dibromocyclopentane. We can represent this in our shorthand way as an alkene plus X2 reacts to yield an alkane with both of the X's on adjacent carbons, trans to each other. X is the halogen chlorine or bromine. And remember, the product is trans because the formation of an intermediate bromonium ion forced an overall anti-addition.
Addition reaction number 4. Cream and sugar in a reactive coffee solvent react to form
The non-fiction version of addition reaction number 4, the halohydrin formation reaction. A halohydrin is a 1,2 disubstituted halo alcohol, which is really just a long way of saying it's a molecule with a halogen X and an alcohol group OH on adjacent carbons. In the presence of water, cyclopentene reacts with bromine to yield trans-2-bromo-1-cyclopentanol. The way to represent this as a formula is an alkene plus X2 reacts in water to yield an alkane bonded to one of the X's and to an alcohol group. Again, the addition is anti.
If you can learn the logic and the patterns in the reactions, you'll be able to master the rest of organic chemistry because you'll be able to predict the outcome of similar reactions with different reactants.
Section B, the next 6 new and exciting electrophilic addition reactions.
Okay, do you remember reaction number 2, the hydration reaction, where an alkene was hydrated in the presence of a strong acid catalyst and water? Well, the crib formula for this was an alkene in the presence of a strong acid catalyst and water reacts to form a neutral alcohol with a proton on the less substituted carbon and an OH group on the more substituted carbon. Well, like we said before, that reaction isn't really a great reaction to carry out in a lab because sometimes the carbocation rearranges itself into something else and you get all these random side products that you hadn't really bargained for, and the yield of desired products ain't that great.
But hydration reactions are important for synthesizing all sorts of commercial chemicals, so the industrial chemical plants use the same type of reaction, only with different reactants. When they do this, they get a larger percentage of desired product. That's good, because the reactants are pretty expensive, so they want to get as much out of them as they can. To do this, they use
reaction number 5, an oxymercuration reaction.
This reaction is called an oxymercuration reaction, and it's the one we told you to remember a while ago when we looked at hydration reactions. The oxymercuration reaction is essentially the same as reaction number 2, only the industrial chemist can use cheaper, easier to get reactants. They carry out the hydration formation reaction using a Lewis acid, mercuric acetate, instead of a strong acid catalyst. The entire reaction is carried out in a mixed solvent system of water and tetrahydrofuran, THF. The THF is just there to help the alkene dissolve. They call the whole thing an oxymercuration reaction.
So in an oxymercuration reaction, we have an alkene in a THF solvent. We treat the alkene with mercuric acetate, HgOAc2. Mercury plus 2 is a Lewis acid, and it's an electrophile. It's no different than H plus in the addition of HX to an alkene, and no different than Br plus in the halogen addition reaction. It just looks a little scarier. Anyway, mercury plus 2 is an electrophile, and as we all know, it's no sweat for an electrophile to add to an alkene.
In the regular old hydration reaction, a carbocation intermediate is formed. But in the oxymercuration reaction, a different sort of intermediate, called a mercurium ion, is formed. This mercurium ion is similar to a bromonium ion in both the way it looks and the way it's formed. The formation of this intermediate is useful because it eliminates those pesky side products that we hadn't bargained for in the acid-catalyzed hydration reactions. We don't get any side products because the carbocation stays put. It doesn't have time to rearrange itself. But like we said, we're not going to talk about why that is right now.
Let's look at an oxymercuration reaction with 1-methylcyclopentene. Remember, in the oxymercuration reaction, the alkene is sitting in a mixed solvent system made up of water and THF with a little mercuric acetate thrown in for kicks. The double bond from the alkene donates its electrons to mercury in mercuric acetate. This in turn causes mercuric acetate to release one of its 2 acetates.
At the same time, the mercurium acetate cation donates 2 of its electrons to the alkene so that single bonds to both carbon atoms of the double bond can be made. Once that happens, the mercurium acetate cation is situated between carbons 1 and 2 in that weird triangular formation we saw just a little while ago when we talked about bromonium ions. This little beauty is called a mercurium ion.
And now water, being the nosy nucleophile it is, butts into the reaction and bonds to the mercurium ion, exactly the same way it did with the bromonium ion. Water bonds to one of the carbons of the mercurium ion. This in turn allows that carbon to give up the electrons it had been donating to the mercurium ion complex, breaking up the weirdo triangular formation. The oxygen in water now has a positive charge, so it releases a hydrogen, a proton, and we now have an alcohol group on the molecule. Plus, the mercury acetate is still hanging around on the adjacent carbon. This freako intermediate, which contains a mercury acetate and an alcohol group, is an organomercury compound. We could isolate it if we wanted to.
But we don't want mercury in the product, and that's what we've got here. Somehow we've got to get rid of the mercuric acetate. And wouldn't you know it, those tricky organic chemists have something up their sleeves. The organomercury intermediate is treated with another chemical, sodium borohydride, NaBH4. Doing that kicks the mercurium acetate out of the way and replaces it with hydrogen from the NaBH4. And hooray! There we have it, an alkane with an OH group, 1-methylcyclopentanol.
Could you tell me a little bit about the class that you took in hydroboration oxidation? That's hydroboration oxidation.
Well, what they talked about was the metals and how oxygen got in and the hydrogenate.
That's right, the hydrogenate. Very good.
The overall oxymercuration reaction looks like this. An alkene in a mixed solvent solution of water and THF reacts with mercuric acetate to produce a mercurium ion, which is similar in structure to a bromonium ion. Nucleophilic water moves in and bonds to one of the carbons of the double bond. The water kicks out one of its protons, leaving behind an organomercury intermediate.
NaBH4 is then thrown into the mix to remove the mercuric acetate group from the organomercury intermediate. The NaBH4 replaces the mercuric acetate group with hydrogen. This leaves us with the final product, an alkane sporting a hydroxyl group. Overall, we added an OH group to carbon 1, and then we added a hydrogen to carbon 2. The final product is 1-methylcyclopentanol.
One more word about the oxymercuration reaction with 1-methylcyclopentene. The. All right, you got me. About 200 more words. The OH group will add to the carbon on the cyclopentene ring, which is attached to the methyl group, because that carbon has the most substituents. Notice how the final product follows Markovnikov's rule and sticks the hydrogen on the less substituted carbon of the double bond, and the OH group on the more substituted carbon of the double bond. The oxymercuration reaction is an electrophilic addition reaction, because the electrophile, mercuric acetate, adds to the alkene in the first step of the reaction.
Even though that oxymercuration reaction was a little more involved than some of the other reactions we've looked at so far, the shorthand version of it couldn't be simpler. We just draw an alkene on the left side of the arrow. And here's where we get to tell everybody that all this complicated stuff is going on.
All of the reagents that are used in the reaction can't be added at once, so we put them on the arrow in order and then number them. On this arrow, we put a number 1 and write in mercuric acetate, HgOAC2, and water, and THF. Those are all the things we're going to add in the first step of the reaction. Then we put a number 2 and write in sodium borohydride, NaBH4, because that's what's added in the second step. Mercuric acetate is the electrophile. Water is the nucleophile. THF is the solvent, and sodium borohydride cleaves the mercuric acetate,
by putting a hydrogen in its place.
This gives us our final product, which we draw on the right side of the arrow. Our product looks just like this. We've got an OH group and a proton on adjacent carbons, and we tell everybody that, hey, my product follows Markovnikov's rule. By saying that to everyone, you're telling them that the proton is on the less substituted carbon, while the OH group is on the more substituted carbon.
And that's it. That's an oxymercuration reaction. If we compare the product of reaction number 5 to the product of reaction number 2, the hydration reaction, we see that both reactions yield neutral alcohols. But remember, the hydration reaction has those nasty little side products, and so isn't really a useful reaction for producing an alcohol. Instead, we can just use the oxymercuration reaction, and we get the same thing, an alcohol.
Okay, so that's all great and good. We got an alcohol product with a higher percent yield. But what if we wanted our reaction with methylcyclopentene to yield a product with a hydroxyl group attached to the less substituted carbon of the alkene double bond, instead of to the more substituted carbon, as we saw in reactions 2 and 5?
And why would I want to do this?
I don't know, but organic chemists came up with a reaction to do it, and it's going to be on your test, so listen up, bucko. Chemists figured out a way to produce an anti-Markovnikov alcohol from an alkene. Anti-Markovnikov is just the opposite of Markovnikov. In a Markovnikov alcohol, the OH group adds to the more substituted carbon, and the hydrogen adds to the less substituted carbon. An anti-Markovnikov alcohol is just the opposite. In an anti-Markovnikov alcohol, the OH group adds to the less substituted carbon, and the hydrogen adds to the more substituted carbon. You can make an anti-Markovnikov alcohol using
Reaction number 6, hydroboration oxidation.
Reaction number 6 is called hydroboration oxidation. Hydroboration oxidation reactions form products which are complementary to oxymercuration products. You'll see why in just a sec. Who are you?
I am Vokinvokram, the arch enemy to Markovnikov.
The product of an oxymercuration reaction, reaction number 5, looks like this, with a hydrogen on the less substituted carbon and the OH group on the more substituted carbon. Basically, in reaction number 6, the hydroboration oxidation reaction, the hydrogen and the OH group switch places. So the OH ends up on the less substituted carbon and the proton ends up on the more substituted carbon.
This is all way contrary to Markovnikov's rule. Let's check it out. In the first step of the reaction mechanism, an alkene and borane, BH3, react to produce an alkyl borane intermediate. We'll explain.
Borane consists of one boron, which has 3 valence electrons bonded to 3 hydrogens for a total of 3 bonds containing 6 electrons. But remember, boron would rather have 8 electrons. It's got an empty p orbital just waiting to accommodate 2 more electrons. The boron, therefore, is a Lewis acid and electrophile, like H+, Br+, and mercury +2. Borane bumps into a juicy-looking methylcyclopentene, which has got electrons and pi bonds sticking way out from the molecule. Borane takes one look, decides it can't resist, and moves in.
As the borane moves in, it builds up a really positive charge on the more substituted carbon of the double bond. Why? Well, because the positive charge is more stable on the more substituted carbon. No big deal, right? That's the exact same pattern we saw on all the other Lewis acids we've looked at. The positive charge is going to pick carbon 1 because carbon 1 has more substituents. And here's the kicker. Borane has to go to wherever the positive charge isn't, which in this case is carbon 2. So, boron ends up bonding to the less substituted carbon.
So we have a positive charge on carbon 1 and boron with a negative charge on carbon 2. But positively charged carbon 1 is not a carbocation.
It's not?
No.
You're sure?
I'm certain.
Then what is it?
I'm getting there. See, I cannot work like this.
We need to count up all the electrons and see what's going on here. Like we said, the boron from the borane molecule is going to bond to the less substituted carbon. It does this so the positive charge that builds up will end up on the more substituted carbon.
As the borane approaches the less substituted carbon, look what happens to boron.
it forms a carbon-boron bond so that there are 2 electrons in that covalent bond. And remember, it's got these 6 other electrons involved in these 3 boron-hydrogen bonds. All of a sudden, it looks like boron is contributing 4 electrons to this huge complex. And we just told you that boron usually only has 3 valence electrons. So, it's got 4. It normally only has 3. All of a sudden, there's a way negative charge on boron.
So carbon-1 over here has a huge positive charge building up on it. And boron over here on carbon-2 has a huge negative charge building up on it. Something's got to be done. Both of these guys want to avoid any sort of charge. So here's what they do.
At the exact same time the borane is moving in on one of the carbons, it boots off one of its hydrogens. But instead of leaving as a proton, as we've seen hydrogen do in the past, it takes the 2 electrons from the boron-hydrogen bond with it. This thing ain't a proton, because it's got 2 electrons. Instead, it's called a hydride. The hydride scoots over to carbon-1 and uses those 2 electrons to form a carbon-hydrogen bond. So, by kicking out hydrogen with 2 electrons, boron avoids the huge negative charge that had threatened to build up on it. And carbon-1 is able to avoid the positive charge that had threatened to build up on it when borane approached carbon-2. And they lived happily ever after and ran off into the sunset.
That's why this molecule is not a carbocation. No carbocation intermediate ever really forms, because the hydrogen and the boron are attaching to the alkane at the same time. The trick is that hydrogen is more electronegative than boron, so the hydrogen pulls the electrons shared in the boron-hydrogen bond more strongly to it. The hydrogens of BH3 behave like hydrides, H-, rather than protons, H+.
So, just to repeat what's going on here, boron from borane is forming a carbon-boron bond to the second carbon. At the exact same time, the hydrogen, carrying both of the electrons from the boron-hydrogen bond, forms a carbon-hydrogen bond to the first carbon. This intermediate, with a boron on the less substituted carbon and hydrogen on the more substituted carbon, is called an alkyl-borane intermediate. Notice that since the boron and hydrogen are adding simultaneously to the pi bond, they wind up on the same side of the ring, cis to one another. The addition is syn because the borane can't reach around and add boron to one side of the double bond and hydride to the other at the same time. Boron is not a contortionist.
Next, hydrogen peroxide, H2O2, with some base like sodium hydroxide, NaOH, is introduced to the mix. We won't go into all the gory details, but basically, H2O2 comes by, kicks out the boron, and replaces it with an OH group. This is the oxidation step of hydroboration oxidation reaction. The H on carbon-1 and the OH on carbon-2 remain cis to one another, meaning they've been added by syn addition.
Let's name the product of this hydroboration oxidation reaction. We've got a 5-carbon ring, cyclopentane, with a methyl group on one carbon and an OH group on an adjacent carbon. The first thing we have to do is number the carbons. The carbon with the hydroxyl group kind of takes precedence over the carbon with the methyl group because the OH group is a functional group. So we number the carbon with the OH group, carbon number 1.
We then number the rest of the ring so that the substituents have the lowest numbers. So the methyl group ends up on carbon-2. So far we've got a 1-hydroxyl and a 2-methyl. But 1-hydroxyl is really repetitive, because we know that the OH will always be on carbon-1. So we can just drop the 1. So the name of our molecule is 2-methylcyclopentanol.
But even though the proton and the OH group that added to the alkene to form the final product added with syn addition, so that they are cis to one another, the methyl group and the OH are trans to each other. So we have to tell everybody that, and we do it by adding a great big old trans to the front of the name.
The final product of the reaction is trans-2-methylcyclopentanol because there's a hydroxyl on carbon-1 and a methyl on carbon-2, and the methyl and the hydroxyl are trans to each other.
But it's important that you remember that the OH and the proton that added to the alkene to form this product added with syn addition. Because of this syn addition, the added hydrogen and the OH group are cis to each other, even though the methyl group and the OH are trans to each other.
The important thing about hydroboration oxidation reactions is that the boron of the borane reactant prefers to attach to the less substituted carbon or with anti-Markovnikov regioselectivity. This alkyl borane intermediate is then treated with hydrogen peroxide, H2O2, and a base, sodium hydroxide, NaOH. The boron is removed from the intermediate and replaced with an OH group in the exact same spot, so that the alcohol ends up on the less substituted carbon and on the same face of the molecule.
The product of the hydroboration oxidation reaction, then, is an alcohol, or trans-2-methylcyclopentanol.
Could you tell me the first time you experienced stereoisomer?
No, I'm afraid I couldn't.
You can't even tell me? Is it too private?
No, because I don't know what it is.
Oh, she doesn't know what it is. All right, well, neither do I.
The shorthand version of this hydroboration oxidation reaction looks like this. We just draw the alkene on the reactant side of the arrow. On the arrow, we draw everything that helped the reaction along, like borane, BH3, THF, which is the non-reactive solvent, hydrogen peroxide, H2O2, and sodium hydroxide, NaOH. Again, since this is a two-step reaction, and since it wouldn't have proceeded the same way if we've added all the reagents at the same time, we have to number the steps. So, once we've got all the reagents listed and numbered on the arrow, we put the product on the right side of the arrow.
The product just has a hydrogen on one carbon and an OH group on an adjacent carbon. But remember, the hydrogen is on the more substituted carbon and the OH group is on the less substituted carbon. So the addition is contrary to Markovnikov's rule, or, as we say, anti-Markovnikov. And remember, the H and the OH undergo syn addition and are cis to each other. And this is what the overall hydroboration oxidation reaction looks like.
Now we know three different reactions which we can use to produce alcohols. The first is acid-catalyzed hydration, reaction number 2, which gives us the Markovnikov alcohol. The second is the oxymercuration reaction, reaction number 5, which also gives us a Markovnikov alcohol. And finally, there's the hydroboration oxidation reaction, reaction number 6, which yields an anti-Markovnikov alcohol.
We're moving a lot faster now, but there's a detailed description of each of these reactions on your insert card.
Pretty soon we'll get into alkynes and all the different reactions alkynes participate in. Fortunately, alkenes and alkynes react very similarly, so that will lighten our load some. But it also means you have to know all of these alkene reactions inside and out.
You're going to need to know each of these reactions and their intermediates, so make sure you learn them. You can find all of them on your insert card. And you also have to do all of your problem sets and get as much practice as possible. Practice, 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 practice. It's all practice! Look, the best way to learn this stuff is to write out each of these reactions using different reactants. Good luck. Okay, our next word is bromo-2-methylpropane.
Has to be gibberish.
No, I'm sorry, Ken. That's an organic chemistry term. You'll receive another mild electric shock for that.
There are only two more types of alkene reactions we have to consider: reduction and oxidation reactions.
Hey, I thought we were doing electrophilic addition reactions. What's with you?
Well, remember in the beginning of tape 2 when we told you there are 4 general types of reactions: addition, elimination, substitution, and rearrangement? Well, there are many other types of reactions that occur in organic chemistry. We're going to look at 2 of those here.
We're talking about reduction and oxidation reactions when we talk about electrophilic addition reactions, because reduction and oxidation reactions, well, they basically fit into the same scheme as addition reactions. We'll explain as we go along. Let's start by talking about reduction reactions.
Reaction number 7, a hydrogenation reaction.
Reaction number 7 is a hydrogenation reaction. The concept of reduction is really simple. Essentially, all we're doing is reducing a double bond to a single bond. Hydrogenation is the addition of hydrogen to an alkene to yield an alkane.
Makes sense, right? We're hydrogenating something. We're adding hydrogen. Adding hydrogen to an alkene reduces the double bond to a single bond, so we reduce an alkene to an alkane. And this is why reduction reactions sort of fit into the scheme of addition reactions. We're adding something to the double bond to reduce it to a single bond.
We're adding to reduce hate! We're adding to reduce hate!
Hydrogenation reactions are carried out in the presence of, well, hydrogen, of course, and a metal catalyst, such as platinum, palladium, or nickel.
Without the metal catalyst, the reaction would be too slow to be of use to anyone.
Say we wanted to reduce 1,2-dimethylcyclopentene to 1,2-dimethylcyclopentane. See the difference in the name? E to A. We're trying to reduce an alkene to an alkane.
All we have to do is mix together 1,2-dimethylcyclopentene, hydrogen gas, and a metal catalyst made of, say, platinum powder.
Hydrogen gas is just a bunch of H2 molecules. The metal catalyst, which is finely divided on the surface of some carbon, has an empty orbital, so it's an electrophile. As the hydrogen gas flows over the surface of the catalyst, the empty orbital in the metal catalyst pulls the electrons in the H2 sigma bond to it. It's like the catalyst lassos the sigma bond and pulls it in. The catalyst breaks the sigma bond between the two hydrogens of the H2 molecule, and then the individual hydrogen atoms form bonds with the surface of the catalyst.
Likewise, as the 1,2-dimethylcyclopentene approaches the surface of the catalyst, the pi bond of the alkene breaks and forms this strange attachment to the surface of the catalyst as well.
So the surface of the catalyst is now covered with single hydrogen atoms and funky-looking 1,2-dimethylcyclopentene complexes. Now here's where the hydrogenation part comes in.
One of the carbons, which had been part of the double bond of the alkene, forms a carbon-hydrogen bond with one of the freestanding hydrogens. Then the second carbon of the double bond also forms a carbon-hydrogen bond with a second hydrogen. Both hydrogens are added to the same face of the molecule, so they end up on the same side of the molecule, on the same side of the plane made up of the cyclopentane ring. So this is a syn addition.
And there you have it, 1,2-dimethylcyclopentane. The new cycloalkane diffuses away from the surface of the catalyst. The catalyst is free to participate in another reaction, and another 1,2-dimethylcyclopentene and H2 molecule move in.
This reaction produces a saturated alkane via syn addition. If a molecule is saturated, all that means is that it's only got single bonds. So since an alkene has double bonds and can be reduced further to make it saturated, we say alkenes are unsaturated.
So once an alkene undergoes an addition reaction to make it an alkane with only single bonds, then that alkane is saturated. And syn addition, we all know what that means, right? That just tells us that the two hydrogens are added to the same side of the double bond. Both hydrogens are added to the face of the cyclopentene, which was attached to the metal catalyst.
The shorthand version of this reaction is: an alkene in the presence of hydrogen gas, H2, and a metal catalyst will react to give us an alkane with the hydrogen on one carbon of what was the double bond and another hydrogen on the adjacent carbon. And we simply note that the hydrogens are cis to one another.
And so even though this reaction is a reduction reaction, it's also an addition reaction because A and B, the alkene and the hydrogen gas, react to yield C, the alkane. Unlike the other addition reactions we talked about, however, the reaction isn't initiated by an electrophile, so the reaction appears a bit different. We're talking about this reaction during addition reactions because we've added hydrogens to the double bond to form a single bond. So, like we said, this reduction reaction sort of falls into the same scheme of an addition reaction.
Finally, the last type of alkene addition reaction we're going to look at is an oxidation reaction. The first step of an oxidation reaction, as you shall see, is an addition of an electrophile to a double bond. And as we all know, that's the first step of an electrophilic addition reaction. That's why we're talking about oxidation reactions now, because the first step of an oxidation reaction is the same as the first step of an electrophilic addition reaction. So simple.
So that said, let's move on to oxidation reactions. Many oxidation reactions form carbon-oxygen bonds, and that's why we call them, well, oxidation reactions. This isn't the technical textbook definition of an oxidation reaction, but for our purposes, it's okay. Technically, what happens in an oxidation reaction is that a positive formal charge builds up on carbon, which then allows nucleophilic atoms like oxygen to come in and oxidize carbon when they add to it.
So although many atoms other than oxygen can bond to carbon during an oxidation reaction, for our purposes, we're just going to keep it simple and say that a carbon-oxygen bond is made during an oxidation reaction.
There are two main types of oxidation reactions that we're going to look at. The first one is pretty simple. It's a hydroxylation reaction, which is just addition with oxidation. If you remember, reaction number 7 was just an addition with reduction. The second type of oxidation reaction is oxidative cleavage of alkenes. Don't stress. We'll get to each one of these, and your mind will be free and easy.
Hi, I would like organic chemists everywhere to know that there are a bunch of freaks who use scary, complicated language to describe arcane things that make my head hurt. Yes.
Okay, the first type of oxidation reaction we're going to look at is hydroxylation, which is an addition reaction with oxidation. So essentially, we're adding oxygen to the double bond. Get it? Addition with oxidation. See?
This reaction is called hydroxylation. Basically, all we're doing is adding 2 OH groups to an alkene. Our product is just an alkane with 2 adjacent OH groups.
Okay, quick note here. In reaction number 7, we looked at hydrogenation reactions, right? And if you remember, hydrogenation involves the addition of hydrogen to an alkene to yield an alkane. So, making a huge leap in logic, hydroxylation is the addition of hydroxyl groups to an alkene to form a saturated compound. Let's see how it works.
Reaction number 8, a hydroxylation reaction.
Basically, in a hydroxylation reaction, 2 hydroxyl groups add to the 2 carbons of the alkene double bond. All of this takes place with the help of the reagent cold dilute potassium permanganate, KMnO4. This hydroxylation reaction produces an alkane with hydroxyl groups on carbons 1 and 2 of the alkane. Both of the OH groups are added on the same side of the double bond via syn addition.
What kind of molecule is this thing? There are 2 hydroxyl groups, one on carbon 1 and one on carbon 2. So we use the prefix di and call the molecule a 1,2 dialcohol. But remember, the OH groups added to the same side of the double bond. We indicate this in the name by calling the molecule a cis 1,2 dialcohol. But instead of calling this thing a cis 1,2 dialcohol, we shorten the name and call the product of the hydroxylation reaction a cis 1,2 diol.
Whew! Thank the Lord. That's so much shorter.
So to write it the simple way, we've got an alkene on the left side of the arrow. On the arrow, we've got cold dilute potassium permanganate, KMnO4. On the product side of the arrow, we've got a saturated compound which contains 2 adjacent OH groups. Those hydroxyl groups are placed with syn addition, and the product is called a cis 1,2 diol.
Nose hair clippers, nose hair clippers, nose hair painting, no cubish painting, yeah!
Okay, so that was reaction number 8, a hydroxylation reaction. And remember, hydroxylation is a type of oxidation reaction because it involves addition with oxidation, which is when the carbon-oxygen bonds form.
Reactions 9 and 10 involve oxidative cleavage of alkenes, which isn't all that complicated. We're just cleaving an alkene, and all that means is we're splitting an alkene up into 2 parts. So, our oxidative cleavage reactions, reactions 9 and 10, break up alkenes into 2 new products. Having said all that, let's look at
reaction number 9, the ozonolysis reaction.
Like we said, ozonolysis involves oxidative cleavage of an alkene, And from this, we get two products.
In the ozonolysis reaction, we cleave an alkene into two parts, using ozone and then zinc dust, which is similar to fairy dust, only poisonous. An ozonolysis reaction looks like this.
When ozone, O3, reacts with an alkene, it completely cleaves the alkene double bond. First, the ozone adds to the pi bond, forming a new product, a fleeting intermediate called a malozonide. It doesn't stay a malozonide long because it's embarrassed by its funny name. This malozonide quickly rearranges itself to form an ozonide. We zap the ozonide with zinc, which reduces it, forming two new products.
We're not going to go into a ton of detail here, but just make sure you know that ozone adds to the pi bond of an alkene, forming a malozonide, which rearranges itself to form an ozonide. And once we treat the ozonide with zinc, we get two, count 'em, two products. Now we just have to figure out what these two products are. It's easy, really. Just find the carbon-carbon double bond and replace it with two carbon-oxygen double bonds, and that's your answer. This will all make sense when we do an example.
The two products that we get depend on what sort of alkene undergoes the cleavage reaction. The two products are usually two ketones, two aldehydes, or one of each. So don't freak out. We're going to tell you what these suckers are right now.
Ketones and aldehydes are similar organic molecules. They both contain a carbonyl group, which is attached to carbon and/or hydrogen atoms.
Okay, great. So what's a carbonyl? A member of the carbonyl family contains a carbon-oxygen double bond. Let's look at this a little more closely. Ouch!
Because they're both members of the carbonyl family, ketones and aldehydes both have carbon-oxygen double bonds. In fact, anything that's a member of a carbonyl family is going to have a carbon-oxygen double bond. The carbon-oxygen double bond is called a carbonyl group. Anytime you hear carbonyl, think carbon, double bond, oxygen. What distinguishes the various members of the carbonyl family is the type of substituents bonded to the carbon of the carbon-oxygen double bond.
The carbonyl carbon of a ketone is bonded to two carbon substituents, while the carbonyl of an aldehyde is bonded to only one other carbon substituent and a hydrogen.
The simplest aldehyde, formaldehyde, has two hydrogens attached to the carbonyl group.
So say we've got an alkene with 4 carbon substituents attached to the double bond. Like we said earlier, all you have to do to figure out the product of the reaction is just split up the 2 carbons on the double bond and give each one of them a double bond and an oxygen. Let's try it.
This reactant has 4 substituents. We cleave it using ozone, followed by zinc dust. The double bond between the 2 carbons is broken in 2, so that the reactant is now in 2 pieces. We give each carbon a double bond, and then we stick an oxygen on the ends of each of the double bonds. And here are the 2 products of the ozonolysis reaction. The 2 products each have 2 carbon substituents on the carbon of the carbon-oxygen double bond, and both products are ketones.
On the other hand, if the alkene has 3 substituents, the 2 products will be 1 ketone and 1 aldehyde. Why? Because there are only 3 carbon substituents to go around, and we have to make 2 products. One of the products will have 1 carbon substituent attached to the carbonyl carbon. That's an aldehyde. And the other product will have 2 substituents attached to the carbonyl carbon. That's a ketone, like we just saw. So, if our alkene reactant has 3 carbon substituents, then the 2 products of an ozonolysis reaction are 1 aldehyde and 1 ketone.
If there were only 2 substituents on the main alkene, the 2 products might be 2 aldehydes, or 1 ketone and 1 formaldehyde. You know formaldehyde.
You want me to cut open what?
Formaldehyde is a member of the carbonyl family, just like other aldehydes and ketones. In formaldehyde, the carbonyl carbon isn't attached to any carbon substituent. It's only attached to 2 hydrogens. So, if our reactant alkene had 2 carbon groups, the 2 products of the ozonolysis reaction will either be 2 aldehydes or 1 ketone and 1 formaldehyde, depending on the placement of the substituents on the double bond.
The shorthand version looks like this. In an ozonolysis reaction, An alkene is cleaved using ozone and then zinc dust. Two products form. They're either two ketones, if there were four substituents on the original alkene, one ketone and one aldehyde, if there were three substituents, two aldehydes, if there were two substituents, or one ketone and one formaldehyde, if there were two substituents.
So like we said, reactions 9 and 10 are reactions which involve oxidative cleavage of alkenes. Reaction number 9 is called ozonolysis, and reaction number 10 is called, well, oxidative cleavage.
Reaction number 10. An oxidative cleavage reaction.
In reaction number 9, ozonolysis, we saw how we can use ozone and zinc to cut an alkene into two parts. But there's another way to do that very same thing, using reaction number 10, an oxidative cleavage reaction. In this reaction, we cleave alkenes using hot potassium permanganate instead of ozone and zinc. Hot potassium permanganate is a much more vigorous oxidizing agent than ozone and zinc, so the reaction goes much further.
When we say hot potassium permanganate, we mean warm, not stolen.
When an alkene is cleaved in the presence of concentrated hot potassium permanganate, the two products formed by the reaction are either a ketone and a carboxylic acid, or a ketone and carbon dioxide from carbonic acid. Which products formed depend on the starting reactant.
We haven't really talked about carboxylic acid yet, so let's see what that is. A carboxylic acid is also a member of the carbonyl family. So, just like we saw with ketones and aldehydes, we know that carboxylic acids contain a carbon-oxygen double bond. But a carboxylic acid is different from a ketone or an aldehyde because one of the bonds of the carbonyl carbon is to a hydroxyl group.
The two products that form as a result of this oxidative cleavage reaction with hot potassium permanganate depend on the reactant alkene. Here's how the products are determined. Let's start with an internal alkene.
You've got a tri-substituted alkene and you treat it with hot potassium permanganate. The alkene is oxidized into a 1,2-diol. Remember those? A 1,2-diol is a molecule with two hydroxyl groups next to each other. Anyway, if the solution, potassium permanganate, is at a high temperature, the reaction doesn't stop with the formation of the diol. Instead, the diol is cleaved, and the products of the cleavage are two carbonyl compounds, a ketone and a simple aldehyde. The ketone stays put, so that's one of our products.
But because the hot potassium permanganate is such a strong oxidizing agent, the aldehyde keeps on getting oxidized. The aldehyde is further oxidized to carboxylic acid, which is product number 2.
So, in total, if you take an internal alkene and oxidatively cleave it with hot potassium permanganate, the two products are a ketone and a carboxylic acid.
Things turn out a little bit differently if the double bond of the alkene is terminal, which means that the double bond is on either of the ends of the alkene chain. The reaction starts out the same. The alkene is oxidized, forming a 1,2-diol. That 1,2-diol is then cleaved, and again we get two carbonyl compounds. The only difference is the two carbonyl compounds are a ketone and a formaldehyde. And once again, the ketone stays put, so that's one of our products. The formaldehyde, however, is further oxidized into carbonic acid. The carbonic acid falls apart, and we get carbon dioxide and water.
So, in short, if a terminal alkene is oxidatively cleaved with hot potassium permanganate, the two products are a ketone and carbon dioxide from carbonic acid.
By the way, carbonic acid is the substance that makes beers, sodas, champagne, and other carbonated beverages bubbly. Carbonated beverages contain carbonic acid. As soon as we pop the top on a cold, smooth one, the carbonic acid equilibrates back into carbon dioxide and water.
Reaction number 8 was the hydroxylation reaction. In that reaction, we used cold potassium permanganate to oxidize an alkene into a cis-1,2-diol. And in this reaction, we used hot potassium permanganate to cleave an alkene into two products. In the first step of the reaction, however, we formed a diol. So the reactions start out the same. The only difference is the oxidizing agent. Cold potassium permanganate isn't as strong an oxidizer as hot potassium permanganate, so the hydroxylation reaction doesn't go as far, and the final product only makes it to a diol.
Hooray! We're finished with alkene addition reactions. Time for a mega review, though. We've covered a lot of material. We're going to give a little summary of the last 6 reactions we just covered. Each of these reactions will be on your insert cards. Once you learn all of these reactions, the rest is all just a cakewalk.
Alkene addition reaction number 5, oxymercuration reactions. We have an alkene and mercuric acetate, HgOAC2, reacting in an aqueous tetrahydrofuran solvent mixture to produce a mercurium ion similar to the bromonium ion. This mercurium ion then reacts with water to produce an organomercury intermediate. Then, the organomercury intermediate is treated with NaBH4, which sloughs off the remaining mercuric acetate group to form the final product, an alcohol, just like we got from a hydration reaction. The OH group is attached to the more highly substituted carbon, which is what we'd predict, knowing Markovnikov's rule and all.
The general chemical formula for an oxymercuration reaction is: an alkene reacts with mercuric acetate and water in a tetrahydrofuran solvent to yield an organomercury intermediate. The organomercury intermediate is then treated with NaBH4 to yield the final product, which has a hydroxyl group attached to the more highly substituted carbon.
But when scientists want an alcohol with the hydroxyl group added in anti-Markovnikov fashion, they use alkene addition reaction number 6, the hydroboration oxidation reaction.
In the hydroboration oxidation reaction, an alkene is treated with borane, BH3, to produce an alkane where the OH group is attached to the less substituted carbon of the original alkene double bond.
As the Lewis acid, borane approaches the alkene double bond. A positive charge begins to develop on the more highly substituted carbon. This encourages borane to simultaneously donate a hydride to the more substituted carbon. Hydrogen peroxide and a base are then added, and the boron-carbon bond is cleaved and replaced with an OH group. The net addition of H and OH to the double bond is syn, meaning they both end up on the same side of what was the double bond.
The final product is an alcohol with the hydroxyl on the less substituted carbon. So, basic chemical reaction, alkene in the presence of BH3 forms an alkyl-borane intermediate with boron on the less substituted carbon and hydrogen on the more substituted carbon. This alkyl-borane intermediate is treated with hydrogen peroxide and a base to form an alcohol with hydroxyl on the less substituted carbon.
Hey, any of this getting through? Huh? You awake? Huh? Any of this sound good?
Alkene addition reaction number 7, hydrogenation reactions. We introduce some hydrogen gas to an alkene and a metal catalyst.
The result is an alkane with 2 hydrogens added to the same side of the alkene double bond.
We can also hydroxylate an alkene, which involves adding OH groups to the double bond of an alkene. In a hydroxylation reaction, 2 hydroxyl groups are added to an alkene by cold potassium permanganate, forming a 1,2-dialcohol or 1,2-diol. The 2 hydroxyl groups are added on the same side of the alkene double bond, which is syn addition.
Now we're into a group of alkene oxidative cleavage reactions called, creatively, oxidative cleavage reactions.
The first type of oxidative cleavage reaction involves an alkene and ozone, O3. Here's a really quick summary of alkene cleavage with ozone. The ozone cleaves the alkene double bond and produces, after treatment with zinc, 2 products, both of which contain carbonyl groups.
The products of this oxidative cleavage reaction are either 2 ketones, a ketone and an aldehyde, 2 aldehydes, or a ketone and a formaldehyde, depending on how many substituents were on the alkene double bond before the reaction took place.
Ow! Are we stopping now?
Oh no, there's no stopping. We're on a roll. We're gonna keep moving. Let's move together.
The second type of oxidative cleavage reaction involves an alkene and hot potassium permanganate. When an internal alkene is treated with hot potassium permanganate, the two products are a ketone and carboxylic acid.
If the reactant alkene has a terminal double bond, however, the two products of oxidative cleavage with hot potassium permanganate are a ketone and carbon dioxide from carbonic acid.
And that's it. We've just finished a huge section of this tape, but we're still in it for the long haul.
Okay, our next word is anti-Markovnikov regiospecificity.
Gibberish!
Oh, I'm sorry, Mary. You lose 250 points and receive another mild electric shock.
Part 2, Alkyne.
Section A, Introduction.
Yeah, new subject. I feel like doing a jig.
All right. As we know by now, an alkene is an unsaturated hydrocarbon containing carbon, hydrogen, single bonds, and at least one double bond functional group. An alkyne is an unsaturated hydrocarbon containing carbon, hydrogen, single bonds, and at least one triple bond functional group.
The general chemical formula for a simple alkyne is CnH2n-2.
We'll talk more about triple bonds in a second. Let's get the basics out of the way first. The first thing we need to do is learn how to name these suckers.
Section B, Naming Alkynes.
Okay, this is going to be a lot like naming alkanes and alkenes, so we won't spend too much time on this. Here are the guidelines for naming alkynes.
First, to name an alkyne, find the longest continuous chain containing the triple bond. Once you've found the longest chain that includes the triple bond, name it. The name of the main chain will begin with the prefix appropriate for the number of carbons in the main chain. The name of the main chain will end in the suffix YNE, indicating that the molecule is a member of the alkyne family. While you're at it, identify and name any substituents on the main chain.
Second, number the carbons of the main chain. What you gotta do here is start numbering the main chain at the end which is nearer to the triple bond. If the triple bond is at equidistant points from both ends, then you just start numbering the main chain at the end nearer the first branching point.
If there are two triple bonds in the main chain, we call the whole alkyne a diene. If there are three triple bonds, we call the whole alkyne a triene.
There may be double bonds in our alkyne as well as other triple bonds. What do we do then? Just number the chain so the double bond has the lower number. Let's try a few, and this will all make sense.
The main chain of this alkyne has 6 carbons, so the name of the main chain is hexyne. The hexyne chain also has 2 methyl groups. Now we need to number the main chain. Start numbering at the end nearer to the triple bond, which in this case is either end. We'll number this main chain from right to left. We need to indicate where the triple bond starts in the name of the alkyne. The name of the main chain becomes 3-hexyne. Now we have to number and name the substituents. The 2 methyl groups are at carbons 2 and 5. The name of this alkyne is 2,5-dimethyl-3-hexyne.
You may have noticed by now that organic chemists present molecules like this in condensed formulas to save space.
When a substituent is in parentheses, that means that it's attached to the nearest carbon to the left. So over here on the right end of the molecule, there's a methyl group in parentheses, and there's a 2 subscript. That tells us that there are 2 methyl groups attached to the nearest carbon to the left. And this methyl group in parentheses in the middle of the molecule is attached to the carbon to its left. Let's draw this molecule out. It'll make more sense.
We'll start with the 2 methyl groups which were in parentheses at the right end of the chain. They go with the first carbon to the left of the parentheses, so we draw both of these methyl groups onto the end carbon of the chain. And the other methyl group, this one over here in the middle, goes with the first carbon to its left. So our molecule looks like this now.
Now we need to name this molecule. The longest continuous chain of carbons, which includes the triple bond, has 7 carbons. The main chain of this molecule is heptenine. The E9 ending tells us that there are double and triple bonds in the main chain.
Do you realize how ridiculous these names are? I mean, Inyine? That's like an Irish singer or something, okay? This is absurd, all right? Do people realize how goofy this is?
Goofiness can be good.
Yes, it can.
Now we need to number the carbons of the main chain. We want the double bonds to have the lowest numbers possible, so we'll number this molecule from left to right.
Our molecule has two methyl groups, one on carbon 3 and one on carbon 6. So far we have 3,6-dimethyl. There's a double bond at carbon 2 and a triple bond at carbon 4 of a 7-carbon chain. The name of the main chain is 2-heptene-4-ine. The 2-heptene tells us that there is a double bond at carbon 2, and the 4-ine tells us that there's a triple bond at carbon 4. When we put it all together, we have 3,6-dimethyl 2-heptene-4-ine.
Section C. Alkyne structure.
Now it's the time you've all been waiting for. That long held off discussion of triple bonds. Oh yeah. The two carbons participating in a triple bond are both sp hybridized. You may remember from the Deep Fried World of Organic Chemistry Part 1 that carbon has 1 2s and 3 2p orbitals, 2px, 2py, and 2pz.
In an sp hybridized carbon, the 2s orbital and the 2px orbital are mixed together to form two hybrid sp orbitals. The 2py and 2pz orbitals are not involved in the hybridization process. The sp orbitals are in a linear arrangement, and the 2p orbitals lie perpendicular to the hybrid orbitals along the y and z axes.
So, when two sp hybridized carbons come together, an sp orbital from each overlaps, forming a sigma bond along one axis. The two remaining p orbitals on one carbon atom are each holding one electron. The p orbitals on each of the neighboring carbons lie perpendicular to the sigma bond. These p orbitals are parallel to each other. The two py orbitals on each carbon interact to form one pi bond, and the two pz orbitals on each carbon overlap and share electron density to form a second pi bond.
So with the overlap of two sp hybridized carbons, we get one sigma bond and two pi bonds. Lo and behold, a triple bond. The other sp orbital on each carbon is used to form another sigma bond to another atom. Now let's figure out where all the electrons are.
The two pi bonds and the sigma bond each contain a pair of electrons, for a total of 6 electrons. The remaining electron from each carbon is in the other sp orbital and is available to form a covalent bond with a substituent.
So, basically, a triple bond has a sigma bond which is surrounded by a cylindrical array of electrons. If we look at an alkyne head-on, all we'd see is a linear molecule surrounded by a core of electron density.
Acetylene is the simplest alkyne. Acetylene is another one of those funky names that's been around so long, it's been accepted as the common name of this alkyne. By the way, an even more common name for this molecule is thyme, like the herb.
Parsley, sage, rosemary, and acetylene.
Acetylene, C2H2, is an example of the linear arrangement we were just talking about. In the formation of an acetylene molecule, one hydrogen bonds to each of the carbons, forming the acetylene molecule C2H2. The carbons and hydrogens all lie along the same axis, and every bond angle in acetylene is 180 degrees.
There are a lot of electrons floating around in this triple bond, and since 4 of them are in pi bonds, alkyne triple bond electrons are very accessible and very appealing to electrophilic passers-by. This makes alkynes reactive toward electrophiles, and at the same time makes them behave in much the same way as alkenes do. Remember all those addition reactions we just reviewed for alkenes? Well, guess what? Because alkynes react in much the same way as alkenes do, they'll also participate in electrophilic addition reactions just like alkenes.
One more important note about alkynes, and then we'll move on to alkyne addition reactions. Alkynes mostly exist in open chains. We won't see many cycloalkynes. See, alkynes have all this strain on them when they're forming ring compounds with fewer than 6 carbons. That strain occurs because of the linearity of the carbon-carbon triple bonds. Because of this strain, cycloalkynes are really rare, so all you need to think about are linear alkynes.
Part 3. Alkyne addition reactions.
We said this earlier, but now we really mean it. We're going to go really fast here. Alkenes and alkynes behave so similarly in addition reactions that you should be able to recall all the underlying forces going on here. What we mean is, if you understand what happens to the electrons as a bromine approaches an alkene pi bond, then you also know what happens when a bromine approaches an alkyne triple bond.
Everything you learned in the first half of this tape is completely applicable to what we're going to talk about here. We're going to assume that you understand terms like carbocation better now. If you don't, maybe you should rewind and check out the section on alkane addition reactions again.
I can't find the remote.
Have you looked behind the couch cushions?
No, I have not.
Okay, alkyne addition reaction number 1. Halogen addition with bromine. The halogen, represented by X2, where X is chlorine or bromine, is added to 2-butene in an inert solvent like methylene chloride. All inert solvent means is that the solvent doesn't get involved in the reaction.
I found it.
This produces the alkene trans 2,3-dibromo-2-butene. We can stop here, but if there are more bromines left to go around, there's also an extremely attractive pi bond left over, ready and willing to participate in another reaction. Another Br2 molecule can move in and further reduce the alkene to 2,2,3,3-tetrabromobutane. All right, we're trucking.
Okay, alkyne addition reaction number 2. Addition of a halo acid to an alkyne. Sound familiar? When we add hydrogen bromide, HBr, to 1-butene, the proton adds to the pi bond so as to give the more stable carbocation. Remember, Markovnikov's rule says the proton will add to the less substituted carbon, so our proton bonds to carbon 1.
This intermediate cation is almost like the carbocations we saw earlier, except that it's on a double bond. We call this carbocation a vinylic carbocation. The bromide anion from the dissociated halo acid adds at the carbocation at carbon 2.
At this stage, we have the alkene 2-bromo-1-butene. We could stop here, but there's plenty more hydrogen bromide to go around, and a juicy-looking double bond right here on this bromoalkene. Another halo acid will attack the molecule until it's totally saturated, and the final product is a 2,2-dibromobutane, formed with Markovnikov regiospecificity. And, in a nutshell, that's halo acid addition to an alkyne.
There are 2 alkyne hydration reactions. Each gives rise to a product sporting a carbonyl group. These reactions are similar to the oxymercuration and hydroboration oxidation reactions with alkenes that we looked at earlier. Hydration reactions with alkynes, just like we saw with alkenes, can form 2 products.
The mercuric ion catalyzed hydration reaction for alkynes is practically equivalent to the oxymercuration reaction of alkenes. That's reaction number 5 on your insert card. This alkyne hydration reaction forms a Markovnikov type addition product because oxygen goes to the more substituted carbon. Let's take a closer look at alkyne mercuric ion catalyzed hydration reactions.
Our alkyne, 1-hexyne, is in the presence of water, sulfuric acid, and a catalyst, mercuric sulfate. There are 2 carbons down here at the end of the alkyne, and the triple bond between them is just ripe for some sort of electrophilic action. A hydrogen adds to the less substituted carbon, and then an OH group adds to the more substituted carbon, forming 1-hexene 2-ol.
1-hexene 2-ol? And they expect me to take this stuff seriously?
This is the Markovnikov product. An OH group has added to the more substituted carbon, and a hydrogen goes to the other carbon. Now there's still a double bond in this molecule, but it doesn't reduce further to give a saturated molecule.
See, this product is an enol, which comes from the suffix "ene," meaning double bond, and "ol," meaning alcohol. And it generally only has a brief existence, kind of like a mosquito. We can also call this enol a vinyl alcohol, meaning an alcohol on a double bond. Anyway, all name-calling aside, enols, as we said, are generally short-lived molecules. We usually aren't able to isolate them in the laboratory.
Instead of another whole addition reaction taking place to convert our enol to a diol, the enol sort of just rearranges itself to create a ketone. This is called an enol-ketone tautomerization. We discussed ketones earlier. They're members of the carbonyl family, with a carbon-oxygen double bond attached to two substituents.
To quickly summarize an alkyne mercuric ion catalyzed hydration reaction, an alkyne in the presence of water, sulfuric acid, and mercuric sulfate reacts to form an alkene alcohol called an enol, meaning it has an alcohol group on a double bond. This enol quickly rearranges itself into a ketone. So, alkyne mercuric ion catalyzed hydration reactions produce ketones.
The second type of hydration reaction is the hydroboration oxidation reaction, which yields anti-Markovnikov products. Remember, we already saw this reaction once with alkenes. In this reaction, an alkyne reacts with a borane, which already has two alkyl groups. This two alkyl group containing borane has a pretty weirdo name, dicyamylborane. So anyway, our alkyne reacts with dicyamylborane, yielding an alkene sporting a boron on the less substituted carbon. This thing is called an alkynylborane.
Does this sound familiar? The hydroboration oxidation reaction with an alkene produced an alkylborane with a boron on the less substituted carbon as well.
Anyway, getting back to our alkylborane, which has a boron on the less substituted carbon of the double bond, it reacts with a solution of hydrogen peroxide and base. The hydrogen peroxide oxidizes the carbon-boron bond by replacing it with an OH group. Depending on where the triple bond was on the original alkyne, the product will either be a ketone or an aldehyde.
If the triple bond is on the inside of the alkyne chain, the reaction will produce an enol, which will then quickly convert to a ketone. If the triple bond of the original alkyne is on the end of the alkyne chain, the reaction will produce an aldehyde.
Now on to reduction or hydrogenation reactions. Just like we saw with alkenes, we can reduce alkynes to alkenes and then again to alkanes using hydrogen with a metal catalyst like palladium.
The palladium catalyst adds two hydrogens on the same side of the first alkyne pi bond via syn addition, producing an alkene. But the alkene is so easily reduced that the catalyst then adds two more hydrogens to produce an alkane.
But what if we didn't want an alkane? What if we wanted the reaction to stop at the alkene phase?
In that case, we could use a special catalyst of nickel boride, Ni2b, which is really good at reducing alkynes to alkenes, but not so good at reducing alkenes to alkanes.
Our alkyne, when reduced with nickel boride and hydrogen, would be reduced to an alkene with both hydrogens on the same side of the double bond, and catalysis would stop right there. A reduction reaction using nickel boride yields an alkene via syn addition. The product is a cis-alkene.
But what do we do if we need a trans-alkene from an alkyne reactant? Well, in that case, we would use another type of reduction reaction, a dissolving metal reduction.
In this type of reduction reaction, the alkyne is dissolved in a solvent, like ethylamine or liquid ammonia. The alkyne is then treated with lithium or sodium.
During the reaction, a hydrogen is added to one face of the triple bond, and then another hydrogen is added to the other face of the triple bond. This gives us a more stable trans-alkene. This trans-alkene is an isomer of the cis-alkene that was just formed during the reduction reaction with the nickel boride catalyst.
We just need to look at one more type of alkyne addition reaction, oxidative cleavage reactions. Jeez!
Just like we saw with alkenes, we can use ozone or potassium permanganate to cleave alkynes into two products.
When we cleave an alkyne using either ozone or hot potassium permanganate, the alkyne triple bond is broken into two. The two products are carboxylic acids.
That's it. We are finished with addition reactions. Now it's time for the addition reaction dance. Really quickly, let's review these alkyne addition reactions.
Alkyne addition reaction number 1. Addition of a halo acid HX to an alkyne. HX and an alkyne react to yield an alkene with H on the double bond carbon with fewer substituents, and X on the double bond carbon with more substituents. The alkene then reacts with HX again to yield the final product, a dihaloalkane with 2 halogens on the more substituted carbon and 2 hydrogens on the less substituted carbon.
In the second addition reaction, a halogen, X2, and an alkyne react to yield an alkene with 2 halogen atoms attached to the carbons of the double bond. The dihaloalkene then reacts with another X2, yielding the final product, a tetrasubstituted haloalkane.
There are 2 alkyne hydration reactions. The first is the mercuric ion catalyzed reaction. An alkyne in the presence of sulfuric acid, water, and mercuric sulfate reacts to yield an enol which quickly tautomerizes to form a ketone. This is a little different from the oxymercuration reaction with alkenes, which produced Markovnikov alcohols.
The second hydration reaction, hydroboration oxidation, involves an alkyne in the presence of a borane, dicyamylborane, and basic hydrogen peroxide. The boron from the dicyamylborane adds to the less substituted carbon, and then the hydrogen peroxide replaces the boron with an OH group. If the reactant is an internal alkyne with 2 different substituents attached to the triple bond, the products of the hydroboration oxidation reaction will be a mixture of ketones. If the reactant is a terminal alkyne, the product of the hydroboration oxidation reaction will be an aldehyde.
Hydrogenation, or reduction, involves the metal catalyst palladium. Hydrogen, H2, is attached to the surface of the catalyst. The catalyst then adds 2 hydrogens to the same face of the alkyne, producing an alkene with syn stereochemistry. Since palladium is a really reactive catalyst, it will further reduce the alkene to an alkane, eventually producing an alkane with 4 hydrogens about the carbon-carbon bond.
When the organic chemists need the reduction to stop after the alkenes are produced, they use the catalyst nickel boride.
When the hydrogen is added to an alkyne in the presence of this catalyst, 2 hydrogens are added to the same face of the double bond, yielding the less stable cis alkene, and their reaction stops right there. It's not reduced any further, and the product is a cis alkene.
If the organic chemists need to produce a transalkene, they use a dissolving metal reaction method in which the alkyne is dissolved in ammonia solvent and then treated with lithium. This yields an alkene with the hydrogens placed on opposite sides of the double bond, which is the more stable transalkene.
Okay, one last reaction and we're finished. This last reaction involves oxidative cleavage of alkynes. When we cleave an alkyne using either ozone or hot potassium permanganate, the alkyne triple bond is broken into 2. The 2 products are carboxylic acids.
Yeah! No more addition reactions ever! We're completely finished with them!
Can you believe it? We finally reached the end of the Deep Fried World of Organic Chemistry, Part 3! Lord of the Kanya!
You know, I can barely believe it myself, but we made it. And we learned a lot of organic chemistry along the way. Don't touch me, please. In this tape, we reviewed 10 alkene addition reactions. We learned all about alkynes, and we reviewed the types of reactions that alkynes participate in. You are a treasure trove of organic chemistry knowledge now.
Thanks for watching, and if you have any questions, give us a call at Cerebellum at 1-800-VCR-REVIEW. We'd love to hear from you.
And be sure to pick up other video course reviews on eye-popping subjects like accounting, finance, psychology, statistics, and microeconomics from
The Standard Deviants!
Bye! We'd love to hear from you.
Notice that we've... I'm sorry.
Than the products, then energy is released.
7, we looked at hydrogenation.
Reduction reactions are
Here with Jesse. Oh, I wish I lived in Jesse's world. Darno, I wish I lived in Jesse's world. Okay.
I'm sorry.
That has to be gibberish.
Yes! No. No!
Called a mercurium.
Both the reactants and the products. Well, I don't.